We're in section 8-3, and we get to be a little weird, so that's kind of cool. And we get to talk about regular singular points. And if we have regular singular points, then obviously we also have irregular singular points. So the first thing we have to know is that we're at a singular point. Once we know we have a singular point, then we have to decide whether or not it's regular or irregular. If I could spell point, and that would be really cool. Last time I looked, it did not have an R in it. Okay, so if we have an equation in the form axy double prime, where ax is a function in x only, bx y prime, where bx is a function in y only, cxy is equal to 0, where cx is a function of y only, then we can change that function to be in the form y double prime plus px y prime plus qx y is equal to 0, where px is just bx divided by ax, and qx is cx divided by a over x. Okay, so we can do that, and then we look at a point, and we're going to look at point a is equal to x is equal to a, at some point x equal to a that happens to be singular. So it happens to be singular, which means I'm dividing by 0. Another way to say that. And now the issue is the point a regular singular point or an irregular singular point? And that's the issue. So we look at the limit as x approaches a of x minus a times px, and we look at the limit as x approaches a of x minus a squared qx, and so we look at both of those limits. If both limits exist, then we have a regular singular point. So if both limits exist, regular singular point. If one of the limits or both the limits don't exist, then the point is a irregular singular point. Now, why do I care about regular singular points? Seems like something that was just made up. Well, if we have a regular singular point at x is equal to a, then I can solve using the series approximation methods that we're using by a method called Frobenius. And Frobenius guarantees, that's a pretty strong word, not used in math very often, but he guarantees there will be at least one solution. So one solution using his method. So now what is his method? Well, first thing is you have to decide that you're at a regular singular point. Second thing you have to do is, well, you're going to use a different set of summation signs. So what you end up doing is you're using y of x is going to be summation n equals 0 to infinity of an x to the n plus r, where r, well, let's back up just a little bit. We have, our answers have been y is equal to a0 plus a1 x plus a2x squared plus blah blah blah. But what if my solution were a is equal to a0x to the 1/2 plus a1 x to the 3/2 plus a2 x to the 5/2 plus blah blah blah. So in what we've done in section 1 and section 2 is that the exponents of the x have always been integers. But what if the exponents of the x are some fractional number that's going up by 1 every time? Frobenius allows us to find those solutions as well. And so that's what we're doing. So now, back to what I said. Y of x is going to be summation n is equal to 0 to infinity, a n, x to the n plus r. And of course, and r can be a fraction. That's perfectly okay. Y prime of x is going to be summation n equals 0 to infinity. Notice that I didn't index the index, n plus r. Why is that? A n x to the n plus r minus 1. Well, if the first term isn't a coefficient, isn't x to the 0, if the first term isn't x to the 0, if I take its derivative, that x to the 0 term still stays there. It doesn't go away. So that's why I have to index from n is equal to 0 again. Y double prime of x, summation n is equal to 0 to infinity, n plus r minus n, minus 1, a n, x to the n plus r minus 2. And so those are the summations that we're going to be using. And so now the question is, what is r? What is r? And so we're going to go and say, well, I've solved the I did my regular singular point thingy, and I said the limit x goes to a is equal to blah blah blah. We're going to call that limit, well, we better say p x px is equal to something, and we have the limit x goes to a x squared qx is equal to something. And in this particular case, we're going to get rid of that, and we're going to assume the singular point is around 0. So we're going to go to 0, and we're going to call this guy p0 of x, and we're going to call this guy q0 of x, whatever that number is. And then, so what we're doing is we're solving for r. This r right here, that r right there, that r right there. That's what we're going to do. And so if we take r minus 1 plus r p0 of x plus q of x and set it equal to 0 and solve it for r, we'll get that r is equal to something. We'll call it R1 and R2. We don't know what it is right now because we just don't know. We don't have a problem. And then I can use those R1s and R2s to solve the series approximation that I'm going to get from using those guys. Isn't that lovely? Yes, I think so too. Okay. Sounds to me like more work than we did in section 1 and 2. But other than that, we're okay, I guess. So now we're going to look at number 4 in the homework problems. Not my homework problems out here is we have 3x cubed y double prime plus 2x squared y prime plus 1 minus x squared. And we want to know whether or not we are at a regular singular point or not. So we rewrite the equation y double prime plus 2x squared over 3x cubed y prime plus 1 minus x squared over 3x cubed y is equal to 0. And we look at the limit as x approaches 0, and we're looking at it at 0 of x, 2x squared over 3x cubed, and we find that that's 2 over 3. And we look at the limit as x goes to 0 of x squared, 1 minus x squared over 3x cubed, and we find that that's a limit. X goes to 0 of 1 over 3x minus x. And we see that that guy goes to 0. This guy does not go to 0. So my limit does not exist for the second limit, and therefore I am at an irregular singular point. Irregular singular point. And because I'm at an irregular singular point, that's good, because I can't solve the original problem using the Frobenius method. And now I don't have to use it. Isn't that lovely? Okay. Now we're going to look at problem number 8. Now, if I was at a regular singular point, I also have to come up with what the r's are. But I don't have to do that because I'm at an irregular singular point. Okay, so number 8, 6x squared plus 2x cubed y double prime plus 21xy prime plus 4x squared minus 1 y is equal to 0. Okay, so I rewrite that y double prime plus 21x over 6x squared plus 2x cubed. Who did that? Somebody messed up. Y double prime. Oh, must be too early in the morning. Y double prime plus y prime plus 4 x squared minus 1 y divided by 6x squared plus 2x cubed. Okay, is equal to 0. Okay, so now I'm going to look at the limit as x approaches infinity. X 21x divided by 6x squared plus 2x cubed. And what am I going to get? X squared goes away. I've got a x here. I'm going to maybe I better go and have the limit go to the right place. That would be cool. 0. Okay, so if I'm going to do that, I'm going to have what am I going to have? 7 over 2. 7 over 2. 3. This guy's going to 0. These guys go away. And I have 21 over 6, which is 7 over 2, which is my P0 of x. And then I'm going to look at the limit as x goes to infinity. No, I'm not. 0, x squared 4, x squared minus 1, 6x squared plus 2x cubed. And I'm going to find that limit, and I'm going to find it as minus 3 over 2. And that's going to be my q0 of x. And then I'm going to go and look for my two r's. R minus 1 plus 7 over 2r minus 3 over 2 has to equal 0. Okay, so I've got r squared minus r plus 7 over 2r minus 3 over 2. Got r squared plus 5 over 2r minus 3 over 2. And it's equal to 0. Equal to 0. I'm going to factor r minus a half, r plus 3 is equal to 0. So there's my 3 over 2. My 6 over 2 minus 1 over 2r is 5 over 2. Okay, so that's good. So r is going to be 1/2 and minus 3. And we probably want to put those in a different order because we normally put them in ascending order. So we'll call it minus 3 and 1/2. Now, Frobenius doesn't say that I have two solutions. I may only have one solution. He guarantees us one solution. So there might not be a solution at minus 3, or there may not be a solution at 1/2, but there will be a solution at one of them. There may very well be a solution at both of them, but that is not something that is guaranteed. What's guaranteed is that I have a solution. Okay. Now we're going to work problem number 18. And hope for the best. Number 18. Oh, that doesn't look too bad. 2x y double prime plus, is it a 3 or is it a 4? 3 y prime minus y is equal to 0. Okay, so I get a 4-0 for writing the problem down correctly. I'm going to rewrite that y double prime plus 3 over 2xy prime minus 1 over 2xy is equal to 0. I'm going to look at the limit. X approaches 0. X 2 over, that's a 3. 3 over 2x, which becomes 3 over 2. I'm going to look at the limit. X goes to 0. X squared minus 1 over 2x. I see that that is 0. So my p naught of x is 2/3. My q naught of x is 0. What's even better is that both exist. Therefore, I'm at a regular singular point, and I can solve this problem using the Frobenius method. And that's basically what is important. I'm going to look for my r's now. r minus 1 plus p naught at x, 3 over 2r plus 0 for my q naught at x. Okay, so I've got r squared minus r plus 3 over 2r, giving me plus 1 over 2r. Okay, and I factor out an r. r plus 1/2, and I find that my r's are going to be 0 and minus 1/2. Okay. If I can control my pen. Okay, so that being the case, now we know the r's. Well, that's good. Back to the original equation. 2xy double prime plus 3y prime minus y is equal to 0. And so now we're going to substitute in for the y double prime and the y prime and the y. So 2x summation n equals 0 to infinity. N plus r. N plus r minus 1. A n x to the n plus r minus 2 plus 3 summation n equals 0 to infinity. N plus r a n x to the n plus r minus 1 minus summation n equals 0 to infinity a n x to the n plus r. Okay, we're going to bring in the 2x summation n equals 0 to infinity n plus r minus 1 a n x to the n plus r minus 1 plus summation n equals 0 to infinity 3 n plus r a n x to the n plus r minus 1 minus summation n equals 0 to infinity a n x to the n plus r is equal to 0. And this guy up here has an equal to 0 on him too. Okay, now we want to make the exponents the same. So I've got 2 that are n plus r minus 1 and 1 that is n plus r. So we're just going to go and, what are we going to do? Well, it really doesn't matter. But we're just going to do this guy. So we're going to let n equal n minus 1. Okay. And we'll keep the other two guys the same. So we have summation n equals 0 to infinity n plus r minus 1 a n x to the n plus r minus 1 plus summation n equals 0 to infinity 3 n plus r a n x to the n plus r minus 1. And then we've got minus summation n equal 1 to infinity and 1 to infinity and 3 n minus 1 plus r a n minus 1 x to the n plus r minus 1 is equal to 0. Isn't that lovely? Okay, so we have an n1, n0, n0. So we're going to remove n is equal to 0. We're going to remove n is equal to 0. And when we get done, everything will be indexed at summation n is equal to 1. Okay, so we will do that. So I'm going to remove n is equal to 0. So let's say r minus 1, a 0, x to the r minus 1, plus, on this guy, 3, n is 0. 3 r a to the 0, x to the r minus 1, plus summation n is equal to 0 to infinity. And I've got, I'm going to put two brackets there. N plus r, n plus r minus 1, plus 3, n plus r, bracket, an, minus 3. How can they both be 3? They're not both 3. There's no 3 here. So it's going to be minus no 3. I substituted in an n minus 1. So that goes away too. Okay. No 3. Minus a n minus 1, x to the n plus r minus 1 is equal to 0. Okay, so in order for that to be the case, some things have to be equal to 0. So r minus 1, a 0, plus 3r a 0 times x to the n minus 1 has to be 0. Okay, so we can get rid of this guy, and then we ask ourselves, can a 0 be 0? Okay, so we know that that r can be 0. So we look at r is equal to 0, 0, 0, 1, 0. So when r is 0, a 0 has to be 0. Because when r is 0, we have minus, no, this is 0, that's 0, the whole thing is 0. Okay, so when r is 0, a 0 can be arbitrary. So that's good. So a0 is going to be arbitrary. a1 is also going to be arbitrary. I don't have any initial condition. And I misspelled arbitrary. And then we have a recurring formula. If I could abbreviate a recurring formula. an is equal to an minus 1 divided by n plus r minus 1 plus 3 n plus r. Isn't that nice? Pretty much. Okay, well, that being the case, we have two cases. Case 1, r is equal to 0. Case 2, r is equal to, and I forget, what is r equal to? Minus a half. We might have solutions in both places. We may only have a solution in one place. Either way would be okay, but I have to do both cases to know. Okay, so in the case of r is equal to 0, my recurring formula becomes an is equal to an minus 1 divided by n minus 1 plus 3n. Minus 1 plus 3n. An minus 1 divided by n squared plus 2n. N squared plus 2n. It would appear that I dropped something on the way. So I'm going to go back and see where I dropped something. And we see a 2 here, and we don't see the 2 there, so we'll put it in. We don't see the 2 here, so we'll put it there. When we removed the n equals 0, there was a 2 there. There's a 2 here. There's a 2 there, which doesn't make any difference. I have the same thing there. But there's a 2 here, which does make a difference. Okay, so there's a 2 there. There's a 2 down there. And there's a 2n squared minus 2n plus, so this would be 2n squared plus n. 2n squared minus 2n plus 3n is an n. Okay, so I think that that is better. Okay, so now we're going to look at my recurring formula. Where does it start? It starts at, let's start, n equals 0. Okay, we're going to start at n equals 0. But that would mean that A1 is an arbitrary. Well, that's fine. We can handle that. Okay, so we're going to start at n is equal to 0. And but if I start at n is equal to 0, I'll get a 0. No, I can't do that either. Where am I starting? Okay, this is 1. Right, I changed the indexing to 1, so I'm starting at 1. This is for all n greater than or equal to 1. Okay, so I'm going to start at n is equal to 1. I'm looking for A1. I end up with a 0 divided by 3. I'm looking at n equal to 2, and I'm looking for n2, and I get A1 divided by 2 squared, 4, 8, 9. 2 squared, 10. I get 10. 8, 9, 10. I get 10. A0 divided by 30. I look at n is equal to 3, and I get A3 is equal to A2 divided by 3 squared is 9, 18, 21. So I get A0 over 30 divided by 21, which is A0 over 600 and what? 630. And then I say, well, maybe that's enough. I could, well, we could go one more, but we'll check that and see if that checks out. And if that checks out, we ought to be okay. So if y of x is a0 plus a0 plus a0 over 2 over 3 x squared plus a0 over 30 x cubed. What am I doing? X squared plus a0 over 630 x cubed. If that's my final answer, then y prime of x would be a0 over 3 plus a0 over 15x plus a0 over 210 x squared, and y double prime would be a0 over 15 plus a0 over 105x. Okay, not a whole lot of terms, but maybe enough to make a difference. I have 2x of those guys. I've got plus 3 of them, and I've got minus of that guy. Okay, so I've got minus 1a0 plus 1a0. That goes away. When I get done, I better have 0. I have minus 1/3 plus 3/5 plus 2/15. Does that equal to 0? Well, I'm pretty sure it does. Let's see. 1/3 plus 1/5 minus 1/3 minus 1/3 plus 1/5 plus 2/15. Okay, well, we multiply this by 3 and I get a 3. We multiply this by 5, we get a 5. 5 minus 5 is 0. Alright, so those guys go away. And now we're looking at the x squared term, and I've got minus 1 over 30 plus 1 over 70 plus 1 over 70 plus 1 over, no, 2 over 105. Okay, so I take out my calculator and I push some buttons and I find those guys are 0, 2. They go away. Plus 0, problem checks. Okay, so that's case 1. Now we have to do case 2. So we're going to go and take the recurring formula and we're going to move it to a different page. Copy. Okay, so now we got the recurring formula. We're still in number 18. And we're doing case 2. R is equal to minus 1/2. And now we find that the recurring formula an minus 1 divided by 2, n plus 1/2 r, n, that's an n minus 1/2 plus 3, that'd be plus 1/2. That'd be minus 1/2. Oh well. Plus minus 1/2 minus 5/2, 3/2, minus 3/2, minus 3/2 plus 3 and minus 1/2. Okay, so that's what my recurring formula is looking like. And, all right, well, we probably should simplify that. A(n) is equal to A(n minus 1) divided by, multiplied by 2, I had n minus 1, n minus 3, plus 3n minus 3 over 2. Okay, so I've got an minus 1 divided by n squared minus 4n plus 3n minus n. I have plus 3 minus 3 halves plus 3 halves. Okay, A0 is going to be arbitrary. And at n is equal to 0, I'm going to have A1 is equal to A0 over 3 halves, which is going to be 2A0 over 3. Well, clearly 2A0 over 3 is wrong, so we have to go back up and figure out where our mistake is. So we'll start erasing some stuff. And it appears that we can come to here. When I multiplied 2 times those guys, I took both the halves out, which is problematic because that would be wrong. So I'm going to try it again. So my 9th grade algebra failed me. An minus 1. You're going to find the same thing. That your 9th grade algebra is going to fail you often. So this is 2n minus 1 times n minus 3 over 2 plus 3n minus 3 over 2. Okay. And an is going to be an minus 1. I've got 2n squared. I've got minus 3 minus 4n minus 4n plus 3n, making it minus 1n, minus n. And then I've got plus 3 over 2 minus 3 over 2 for nothing. Okay, and then I'm going to look at what is, at n is equal to 1, what is A1? Well, A1 is going to be A0 divided by 1. And at n is equal to 2. A2 is equal to A1 over, n is 2, 4, 8, 6, which is going to be A0 over 6. And at n is equal to 3, I have A3 is equal to A2 over 9 times 2 is 18. 3 squared is 9. Times 2 is 18. Minus 3 is 15. So I'm going to have A0 over 90. Okay, and that might be enough to check, so we're going to check. Would probably have you on a test find A4 as well, just for the heck of it. Okay, so y is going to be A0 x to the 1/2. Because r is 1, wait a minute, x is r is minus a half. So a0 x to the minus 1/2 plus a1, which is a0 x to the 1/2 plus a2 a0 over 6 x to the 3/2 plus a0 over 90 x to the 5/2. Isn't that just lovely? Okay, and then I've got y prime minus 1/2 a0 x to the minus 3/2 plus 1/2 a0 x to the minus 1/2 plus 1/4 a0 x to the 1/2 plus, let's see, 5 goes into 90. 18 times. 18 times 2, so it'd be 90 divided by 18 times 2, which would be 36, x to the 3/2. I'm thinking. Okay, so y double prime plus 3 over 4 a0 x to the minus 5 over 2 minus 1/4 a0 x to the minus 3/2 plus 1/8 a0 x to the minus 1/2 plus 3 goes into there, 12 times 2 is 24, a0 over 24 x to the 5 over 2. Isn't that lovely? Okay, and we want 2x of that one, and we want 3 of that one, and we want minus 1 of this guy. Okay, so if I look at 2x, so I'm looking at the minus 5 halves x term, and I got 2 of them, so that means I have 3 over 2, and I have minus 3 over 2 that go away. And now I'm looking at the x to the minus 1/2 term. I have minus 1, I have minus 3/2, and then, no, I have plus 3/2. Minus 1, minus 3/2, minus minus 1/2. 1/2 minus 3/2 plus 3/2. So that term goes away. Boom, 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 plus 0. Now I'm looking at the 1 x to the 1/2 term. Minus 1 plus 1/4 plus 3/4. That term goes away. Now I'm looking at the 3/2 term, minus a 6 plus a 12 minus 1/6 plus 1/12 plus another 1/12. So that term goes away. 0. So my problem checks. And we're done with problem 18. We're now going to problem number 26. And maybe, just with a little bit of luck, I can get more of it right the first time through. 2xy double prime plus 1 minus 2x squared y prime minus 4xy is equal to 0. Okay, so I'm going to look at the limit. X approaches 0 of x 1 minus 2x squared over 2x. And I see that that's 1/2. And I'm going to look at the limit. X approaches 0, x squared 1 minus 2x squared over 2x. And I see that that's 0. Okay. Both exist. Both exist. Therefore, I'm at a regular singular point, and the Frobenius method will work, so I can continue. And my P naught at x is at 0. P naught at x. Well, that's redundant. P naught. Regular singular point. My P naught is 1/2. My Q naught is at 0. I'm looking at r minus 1 plus 1/2 r plus 0 is equal to 0. So I have r squared plus minus r squared minus 1/2 r is equal to 0. I can factor r out. R plus 1 minus, oh well, r minus 1/2 is 0. Therefore, r is going to be 0, and r is going to be 1/2. Okay, so I know my r's. Now I write down my summation stuff and solve for recurring formula. Okay, so I've got 2x summation n equals 0 to infinity n plus r minus 1 a n x to the n plus r minus 2 plus 1 minus 2x squared summation n equals 0 to infinity n plus r a n, better put parentheses, x to the n plus r minus 1 plus, or is it minus? Minus 4x summation n equals 0 to infinity a n x to the n plus r is equal to 0. So making the assumption that I did that right, let's say 2x, 1 minus 2x squared minus 4x. Okay, so we're going to bring everything inside the summation signs. We're going to have summation n is equal 0 to infinity 2 n plus r minus 1 a n x to the n plus r minus 1 plus summation n equals 0 to infinity n plus r a n x to the n plus r minus 1 minus summation n equals 0 to infinity 2 n plus r an x to the n plus r plus 1. So that's pretty weird. And then we still have another minus summation n equals 0 to infinity for an x to the n plus r plus 1 is equal to 0. Okay, so I got 4 summation guys. What am I going to do about it? Well, I'm going to go and do a substitution. N equals n minus 1. No, minus 2? And then, yeah, minus 2. Substitution, n equals n minus 2. And then all of my indexing will be the same at that point. Okay. The other thing I'm going to do, well, I'm not really too full yet. Alright, so I'm going to get summation n equals 0 to infinity to n plus r. No, I'm not going to do that. I'm going to, oh yes I am. Yeah, I'm doing exactly what I want to do. Okay. Summation n equals 0 to infinity to n plus r minus 1 an x to the n plus r minus 1 plus summation n equals 0 to infinity n plus r an x to the n plus r minus 1. Okay, now I'm going to do the two substitutions. Minus summation n equal 2 to infinity to n minus 2 plus r an minus 2 x to the n plus r minus 1 minus summation n equal 2 to infinity for an minus 2 x to the n plus r minus 1 is equal to 0. Okay, so we're going to start a new page, hope that everything above that line is perfectly okay, and if it's not, then we'll have to worry about that later, won't we? Paste. Okay, so we'll get rid of this substitution guy. Okay, so the next thing we're going to want to do is remove the 0th term. The 0th term and the 1 term from that guy, and we want to remove the 0th term and the 1 term from that guy. And then we'll have summation n equals 0 to infinity. Isn't that a good idea? Okay, so the n is equal to 0 term. So I have 2 r minus 1 a0 x to the r minus 1. I'm going to remove the first term, the 1 term, plus 2 and r plus 1 r, because the 1 minus 1 goes away, a1 x to the n. Okay, now I'm going to remove the 0 guy from him, plus r a0 x to the r minus 1, and then the 1 term from him, plus r plus 1 a1 x to the n plus summation n equals 0 to infinity. double brackets. Okay, I've got 2 n plus r, n plus r minus 1, plus n plus r, an. Then I've got minus 2, n minus 2 plus r, plus 4. See, there's a minus sign there, a minus sign there. It's sitting here, and that's why I can do that. A n plus 2 is equal to 0. Okay, isn't that nice? All right, so what do I know? I know that 2r, r minus 1, a0 x to the r minus 1, plus r, a0 x to the r minus 1 has to be 0. Okay, so I know that. That being the case, x to the r minus 1 isn't 0. So I've got 2n, n minus 1, plus r. These are all r's. R, a 0 has to be 0. Okay, so if I put in an r, if I put in 0, so my r's are not that r. We know that our r's are 0 and 1/2. So if we put in 0, we get 0, a0 is 0, so that's good. If we put in a 1/2, I've got a 1/2, I've got a minus 1/2, I've got a 1 minus a half plus a half. That's 0 too. So a0 is arbitrary, and both r's work in that situation. So that's good. I'm now going to look at my a1 term, and I have 2 r plus 1 r a1 plus r plus 1 a1 is supposed to be 0. Okay, so I've got 2r squared plus 2r plus r plus 1 times a1 has to be 0. I have 2r squared plus 3r plus 1 times a1 has to be 0. I put in a 0 and I don't get a 0 unless a1 is 0. I put in a 1/2 and I don't get a 0 unless a1 is 0. That implies that a1 is going to be 0. And that I have a recurring formula. And now the issue will be, can I see my recurring formula? And we'll get this a little smaller so I can see so I can write down my recurring formula. And my recurring formula is going to be a(n) This is an minus 2. I have an an plus 2 there. How inconvenient. An minus 2. So my recurring formula is going to be an is equal to 2 I don't really need that bracket. 2n minus 2 plus r plus 4 an minus 2 divided by 2 n plus r n plus r minus 1 plus r plus n. Alright, so that's my recurring formula. And with a little bit of luck, that's right. Alright, well, we're going to do some algebra and hope for the best again. I have 2n. I have 2n plus r, and I have minus 4 and plus 4, so it goes away. On the bottom, I have n plus r times, I have an n plus r here, an n plus r there. I can bring it out. I can bring it out, and then I can have, well, I won't do that. What I'm going to do, I'm going to write the same thing down. 2n plus r, n plus r minus 1 plus n plus r. Okay, so I've got an n plus r there, I've got one there, I got one there, which leaves me a 1 left over. And so I'm going to have a 2 on top, a 2n plus 2r minus 2 plus 1 minus 1. an minus 2. an minus 2 for my recurring formula. Okay. Looking very nice. Case 1. So what we'll do, an, and we're filling up the page, it's pretty full. So we're going to go back, view, zoom, wrong way, view, view, full screen, zoom. We'll go back out to, no, we can't go up to 200%. View, zoom, 150. Okay. So now we're back to where we were. We're going to take the recurring formula and put it on another page. We're still doing number 26. Okay, case 1. R is equal to 0. A0 is arbitrary. A1 is 0. My recurring formula becomes an is equal to 2, an minus 2 divided by r is 0, 2n minus 1. 2n minus 1. For all n greater than or equal to what? 2. Why is it 2? Why is it 2? Because our summation is 2 to infinity. Where is our summation? 2 to, right here. 2 to infinity. That's supposed to be a 2. Alright, so that's why it's 2. Okay. A1 is arbitrary. Okay, n is equal to 2. N is equal to 2. A2 is equal to 2. A0 divided by 3. Okay, 2 over 3. A0. At n is equal to 3, A3 is equal to 0 because A1 is 0. N is equal to 4. A4 is equal to 2. A2 divided by, I put a 4 there, I get an 8. I subtract 1, I get a 7. So I've got 2 over 7, 3 over 2. 2 over 3, A0, so I have 4 over 21, A0. Okay. And then I've got n is equal to 5. A5 is 0 because of whatever. And then n is equal to 6. A6 is equal to 2. A4 divided by 6 times 2 is 12 minus 1 is 11. 11. So I got 2 over 11, 4 over 21, A0, which is equal to, okay, so that's going to be 8 over 231, A0. Well, that ought to be enough terms. So y is equal to A0 plus A2, which is 2 over 3 x squared, because we're skipping the odd terms, plus 4 over 21 x to the 4th, plus 8 over 231 A0, 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 x to the 6th. And if we look in the back of the book, we see that that checks, so we will move on to the second case. And the second case is case 2. R is equal to 1/2, I think. Still, yeah, 1/2. My recurring formula becomes AN is equal to 2 AN minus 2 divided by 2n minus plus 1/2 minus 1. So my recurring formula becomes AN minus 2 over n for all n greater than or equal to 2, but the A1 is still 0, so all the odd guys are still going to be 0. So AN is equal to 0 for all odd. Alright, that being the case, we have n is equal to 2. A2 is equal to 2 A0 divided by 2. That was good. Looked at the wrong one. So that'd just be A0. N is equal to 3. A3 is 0, so we don't have to do anything. N is equal to 4. A4 is equal to 2. A2 divided by 2A2 divided by 4/3. 4.5. N is equal to 4. Well, n is equal to 4 right there. Use this guy again. So over 4 which is a0 over 2. Oh well, let's try again. We're looking at two different formulas and trying to get the same thing. So we're going to go and look at this guy always. So a2 is equal to a0 over 2. Much better. a4 is a0 over 2 divided by 4, which is a0 over 8. N is equal to 5, a5 is 0. N is equal to 6. a6 is equal to a4 divided by 6, which is a0 divided by 42. 48. If I could do my math right, 48. All right, final answer. Y is equal to a0 x to the 1/2 plus a2, which is a0 over 2, a0 over 2 x to the 5/2 plus a0 over 8 x to the 7/2. And why did I go to 5? That's obviously 3. I have to add 1. 3, 5, plus a0 over 48 x to the 7/2 plus other things that I don't have. Okay. Should we check that? Or should we just say that it's right? Now we'll just say it's right. So we're going to say check by back of book. Okay. And that ends our video of section 8-3. And oh, by the way, there will be a Frobenius problem on your test. So. Okay.